Chapter 10, Material Properties, Richard J. Murphy, Ph.D. Introduction. Chapter intended to review the important basic concept of the material science. The representation of various content areas assumes that most of the topics have been covered in the full course of material science. It may be useful to use the text from that course as accompanying with the review presented here. Chapter follows conventional order of topics, begins with the atomic structure, following bonding, crystallography, phases, equilibrium. After section, various metallurgy, solid solubility, diffusion, corrosion. Various behaviors are covered mechanically, magnetically, electrically. Finally, there are brief reviews of polymers and composites. Alright, atomic structure, bonding, crystallography, phase, equilibrium, ferrous metallurgy, solid solubility, metal oils, chemical diffusion, corrosion, mechanical behavior, magnetic behavior, electrical behavior, engineering materials, and summary. Alright, atomic structure. Atomic structure of an atom involves the spatial and energetic arrangement of electrons of the atom. The nucleus is not included with the description of atomic structure of the arrangement of the electrons, not arrangement of the atoms. Atomic structure is important to remember that atomic structure refers to the arrangement of the electrons in an atom, not the arrangement of the atoms. The atom arrangement is the crystal structure also is all about. For each atom, the number of electrons, number of the protons matched with the atomic number of the electron or particle with a constant motion around with the nucleus by virtue of the dual nature of their also with the wave the electron passes energy due to their motion of the mass velocity with their wavelengths, because wavelength of the electron must be an integral fraction of the path of the link of the electron, and ground nucleus energies of the electron in an atom are not spread over a range of values. They are limited to specific values with no possibility of intermediate energies. The characteristic is what with neutralization. Later refinements of the atomic theory expanded with many of the early concept of the electronic occupied with the energy levels in such a way that no more than two electrons can have the same energy, occupy the same orbital. Thus must have the different spin. But this rule is called the Pauli's exclusional principle. Gross quantization is designated by the principal quantum number n. N is equal to whatever nth number. The energy of each level according to the Bohr's atomic model is given in equation 10.1. Energy is equal to 13.6 Z squared over nth squared times energy V. Alright, Z is the atomic number of the ends of the principal quantum number of the energy level. The electrons excited with the energy level. The energy absorbed, the magnitude of the energy absorbed. This is the difference between the two energy levels calculated using the equation. Energy level is equal to energy level 2 minus energy level 1, or 13.6 over the atomic number squared, 1/2 over 2 squared minus 1/2 over 1 squared, and then U equals your equation. The calculated the difference between the two energies. Wavelength radiation absorbed with electronic excitation can be then determined by as wavelength radiation as in Planck's constant and the velocity of light over the energy absorbed. With the energy level designated by each value of the n with a further quantization of the energy and indicated by the letters S, P, D, F. In order, increasing energy with the subsequent quantization are called orbitals, not orbits. It is the level that the common connection is made between the electron energy with the special distribution. Energy level designation of the representative of the elliptical symmetrical distribution probability location of an electron as shown in figure 10.1a. The P levels are actually comprised of three separate with a mutually perpendicular dumbbell-shaped probability distributions. Each level parallel to the X, Y, Z axis is shown in figure 10.1b. Each orbital can contain up to two or only two electrons. The reinstatement of the Pauli's exclusional principle, each orbital can contain no more than two electrons, and those two electrons must have the different spins. 4s orbitals fills the 3d orbital. The orbital notation can be used to identify energy level of each electron in the atom is seen. Table 10.1, electron configuration of the first 30 elements. So it goes from 1s1, 1s2, 1s2, 1s1, 1s2, 2s2, 1s2, 2s2, 1sp, and then the p has 6 orbitals, and 1s2 at 1, 2s, and then it continues back to 1s2, 1s2, 2p, 6x, 3s1. 3s1 continues for 2 orbitals, and then and then it goes 1s, 2s is 2p, 3s is p's for 3p, 6, and then finally get into D and 4s. Alright, table of 10-1 in electron configuration, magnitude with the nth given the first of the followed with the designation S, and if the property with a P and D. Number of electron orbital designations with this energy is shown in superscript. The sum of the superscript is therefore the number of electrons in the atom. 10-2 bonding. Material behavior largely determined by the type of the bondings that occur with among various types of material. In some cases, the molecules exist. More important bonds may be those with among molecules. Usually, strong bonding called interatomic bonding occurs between atoms. There are 3 types of interatomic bonding: covalent, ionic, and metallic. Each takes place because of the specific added aspects of the structure of the atom. Covalent bonding: consider the hydrogen atom of the atom with 1 electron type of the type S of the designated 1s1. Remember that the s orbital is the elliptical cloud probability location thereof. If the atom is in vicinity of another hydrogen atom, the electron in the second atom can occupy the s orbital, but the first atom becomes the 2 orbitals overlaps in some extent and can be shown by advanced calculations that total energy of the pair atoms of both the s orbitals with sharing 2 electrons is lower than the sum of the energies of the 2 atoms taken separately. The fact indicates the 2 atoms would rather be together. This is bonded than apart, but the 2 atoms cannot overlap completely because of the strong repulsive force of the 2 nuclei. Therefore, the 2 atoms assume the equilibrium separation balances of the attractive and the repulsive forces of the total energy correspond curve represents the bonding event of the 2 atoms. Is shown in figure 10.2. In this case, the third hydrogen atom approach close enough to overlap the s orbitals with the first 2 atoms to provide with the third electron. So the s orbital with the Pauli's exclusional principle states that orbital can have no more than 2 electrons. Therefore, the third atom cannot enter into the bond relationship with the pair that must move on. Thus, the reason is hydrogen gas exists if the atomic molecule. Covalent bonding can be defined with the bonding occurs with the atoms that are half-filled orbitals. For instance, with the chlorine with the atomic number of 17, atomic structure 1s2, 2s2, ps6, 2ps6, 3s2, 3pf5. Notice that each orbital is filled with the 2 electrons except one of the 3p orbital with a half-filled. This is a covalent bonding orbital, but it can be a half-filled orbital of any other atom, for example, another chlorine atom, and this is the reason why chlorine gas exists in diatomic module. Molecule. Carbon has 2 filled half orbitals with a configuration unfavorable, forming 3-dimensional network of bonding carbon atoms in an excited state. However, the carbon atoms can possess 4 half-filled bonding orbitals. Therefore, by forming a covalent bond, 4 neighbors also have the bonding orbitals. This has how a diamond, silicon, methane, carbon tetrachloride form, as well as carbon-carbon bonds and polymers. This type of the bond is very strong. Figure 10.2. Ionic bonding. Ionic bonding consists of electrostatic attraction between oppositely charged ions. Ions are atoms that have lost gained electrons, giving them positive and negative charge. Fine ions are formed most easily with the atoms that have the s electrons highest energy level, other than 1 or 2 electrons short filling, and of the p orbitals. In the former cases, the s electrons can be excited away from the atom, leaving the positively charged ion of the sodium and calcium 2 plus. Later cases of the atomic can attract with the extract free electrons completely filled with the p orbitals, give it the negative charge ion in fluoride and oxygen. Measure of the ease of which atoms attract the electrons to make negative ions is called electronegativity. Atoms on far left of the periodic table, so if the sodium and calcium low electron negativity is considered electropositive. For the atoms far right, so is fluorine, oxygen, high electronegativity. These ions with the opposite charge of the present together, they can experience strong electrostatic attractive forces. which imbalance or repulsive force for the nucleus interaction result in large net bonding energy. The larger the difference for the electronegativity, the stronger the bond. The equilibrium of the bonding energies is shown in figure 10.2. Metallic bonding occurs when the materials whose atoms have the s electron with the highest energy electrons. Many of the atoms of this type are together. The energy system is lowered, and by process in which s orbitals overlap and the s electrons become free from the atoms move throughout the material, while the electrons of the ion cores remain strongly bound with the type of the bonding, giving rise to the common metallic property with the high thermal electricity conductivities. It is not easy to compare the relative strength of the third type of the bonding in general. However, the average bond strength with an increase of the order metallic, ionic, covalent, all three types of bonding with a comparison to the much weaker intermolecular bonds. Alright, 10.3, crystallography. Arrangement of the atoms of the system material fall into the two general type classes: entirely periodic, predictable, or reproducible, and quite random. Number 2. First arrangement characteristic of the crystallology, with the second is found with the amorphous solids, usually referred to as glass. Arrangement of the atoms on the crystal, subject of crystallography. Bravais lattice. Subject to the simplified, consider the arrangement of the points of space and lattice rather than of the atoms. It has been shown that there are 14 ways of arranging points in space so they satisfy with the symmetry reproducing periodically from a crystal. Shows some of the crystallities. Requires these arrangements called the Bravais lattice. 3 lattices of the important structure of the metals: face-centered cubic (FCC) and body-centered cubic. Simple hexagonal with the first 2 common metals, 1 part per lattice point. Lattice is also known as a form of a hexagonal closed pack, or the HSCP. Simple hexagonal 2 atoms lattice point, and 3 lattices are shown in figure 10.3. Expanding the lattice point until the 2 touch of as a sphere in contact, much like when familiar with a ping pong ball model can prove another view of the cubic crystal. Coordination. Number of the neighbor spheres shall each sphere's context the FCC crystal in the number 12. These can easily be seen with the constructing of the closed pack plane in which each sphere is in contact with 6 neighbors. When a similar plane is brought with the contract of the first plane from above, the 3 additional spheres coming into contact with a similarly 3 in contact from below. 6 plus 3 plus 3 is 12. For the BCC coordinated number 8, it must be easily determined by observing the 8 corner spheres in contact with the body-centered sphere. The distance between the neighboring atoms called the nearest neighbor distance. Spheres in the contact represented with the 2 radiuses as a 2 radius, where radius is sphere representing atomic radius, and this is the nearest neighbor distance, which can be written in from the last parameter A in the cubic system. The FCC at 4 radiuses at A times the square root of 2, where 4R represents facial diagonal, as does A the square root of 2. Therefore, 2R is equal to A square root of 2 over 2, equal to A over the square root of 2, and radius is equal to A over the 2 times the square root of 2. BC, 4 radius at A is to square root of 3, represents 4R, represented with a cubic body diagonal, as does the square root of 3. Therefore, 2R is equal to A to the square root of 3 over 2. Radius is equal to A over, square times the square root of 3 over 4. One most important concept of the need for the number of atomic per cell unit. This is determined as shown below using the figure 10.3. Since unit cells are tracked with the infinite array, each unit cell is connected to the other unit cells as all sided. Hence, 8 other unit cells can share each corner atom. Therefore, number of corner atoms is equal to 8 corners over 8 unit cells, or equal to 1 corner atom at 1 unit cell. The FCC 2 cells shall have either face-centered atoms. Therefore, the number of face-centered atoms is equal to 6 face-centered atoms over 2 face unit cells, and 3 face-centered atoms over 1 unit cell. Since the FCC numbers of the atoms per unit cell is 8 over 8 plus 6 over 2 is equal to 4. The BCC number of atoms per unit cell is 8 over 8 plus 1 body-centered atom at number 2. Example in solutions. Alright, density calculation. It is not a simple process to calculate the density of the crystalline element. The equation of the density is simple. The only information needed for the type of the structure is mass atoms unit cell with the volume of the unit cell. mass of the the density is equal to the mass over the volume times the grams over centimeters squared. The mass of the atomic unit cell with the productive mass each of the atom and number n's for the atom unit cell with the mass each unit of the gram atomic weight or GAW weight in grams of the 1 mole of atoms divided by the Avogadro's number. M mass of the atom of the unit cell is equal to the number nth over the gram times the gram atomic weight over 6.023 to the 10th 23rd 10 to the 23rd times grams. Volume over the unit of the cell of the cubic structure of the cubic lattice parameter is A to the third. The volume can also be obtained from atom radius using equation 10.4 and 10.5. BCC volume is equal to 4 radiuses over the square root of 3 to the third. The FCC volume is equal to 4 radiuses over the square root of 2 to the third. Crystal structures, atomic mass, atomic radii, density of the 4 cubic structures are given in Table 10.2. Data selected crystals, crystal structure, atomic mass, AUMU, and atomic radius NM, and density grams of centimeters. Or atomic packing factor is the volume of the atoms in a unit cell divided by the volume of the unit in cell. The FCC is the atomic packing factor, 4 times 4 over 3 times the pi for the radius to the third over the a to the third equals 4 times 4 to the third a square, 4 times 4 thirds times pi to the radius third over 4r over 2 squared to the third. BCC is atomic packing factor is 2 times 4 over the 3 times pi to the radius to the third over a to the third, or equal to 2 times 4 over 4 thirds times pi to the radius third divided by 4r over the third over the square root of 3 to the third, equal to the square root of 3 pi over 8. Miller indices language of crystals. Describe the plane with the direction cubic crystal special notation of the Miller indicator that it had been developed with a method of determining indices of the plane as follows. Draw a plane that it does not pass through the origin of the unit cell. 1. Construct the cubic unit cell with a rectangle of the coordinate system x, y, and z. Draw the plane and intercept the unit cell in such a way that it does not pass the origin. 2. Note the intercept of the x, y, and z axes and integers and infractional multiplies the cell edge designated with the numerical values a, b, c respectively. 3. Take reciprocals of the a, b, c. Call these values h, k, l represented and include the reciprocals h, k, and l parentheses name of the plane. For example, the plane is parallel to the z-axis and z-intercept. C is infinite. Therefore, reciprocal of L is 0. Method of determining indecisive of the crystallographic discretion somewhat different. Draw the direction over the pass through the origin of the unit cell. 1. Construct the unit cell with the XYZ coordinate system. Draw the direct interest within the unit cell in such a way that it passes through the origin. Determine the XYZ coordinates as the point over which direction intersects the cell away from the origin. Designate with the integer with a fraction multiples of the length of the cubic edge. Close coordinates x, y, and z brackets with the name of the direction. For example, the cubic edge 101, 110, and 001. And goes into example and solution. 10.4 phase equilibrium. The relationship among the phase of the material strictly governed by the thermodynamic variable, the temperature of the T with the P for pressure of the phase composition relative to the amounts components in solution with the phase. The relationship is summarized with the equilibrium phase diagram shown with the 1 atmosphere pressure with the addition with the temperature of the alloy composition of various phases. Stable equilibrium, for example, the fifth is the equilibrium phase of the copper-nickel system with traces across the diagram at 1000 degrees Celsius. You find only one phase of the alpha composition with a solid region at 1200 degrees Celsius. Transverse diagram begins with the liquid phase designated to L, then enter the remaining region containing liquid and alpha. Concludes alpha with the alpha phase. This means that the copper-nickel system is 1200 degrees Fahrenheit liquid phase, stable over range composition up to the boundary with a two-phase region called liquidus. All it means if the alpha phase is stable over the range of composition, pure nickel back to the boundary with a two-phase region called the solidius, and that within two boundaries with the two phases, liquid and alpha are in equilibrium. It is the two-phase region. The inverse lever rule must be applied with the gain information inside of the region. To inverse level the rule, you determine the relative amounts of phase two-phase region. Now consider figure 10.6 to analyze the copper. Nickel system at 1200 degrees Celsius. You draw the horizontal line, cover the tie line through the two-phase liquid plus solid region with a boundary next. End points with the two lines with an indicated composition with a two-phase with equilibrium when the composition called the phase composition are red and traced down with a horizontal axis phase with a diagram. If alloy composition chosen falls within the endpoints of the tie line at 1200 degrees Fahrenheit Celsius, you know the phase diagram of the alloy consists of two phases with a determined amount of the phase of the alloy applying with the inverse level of the rule labeled the alloy in composition C0 with the composition solid with CS composition C of liquid CL. The relation for the fraction of liquids are given by equation 10 and 11. Fraction of the liquid is equal to composition solid over the alloy, composition solid time minus the composition alloy over the composition solid over the minus the composition liquid. Notice that the equation simply relate for the segment of the tie line entire length of the tie line relation for the inverse sense. If you are interested in the fraction of phase for the left, then take the ratio of the right-hand segment of the tie line with the entire length of the tie line. If, however, you are seeking fraction of phase for the right, you need to take the left-hand end tie line and compare that in the entire length of the tie line. The inverse lever can be used with the two-phase region in a phase diagram. It does not matter how complex the phase diagram. Fraction liquid plus fraction solid equals 1. Alright, we got solutions. Some materials exhibit the diagram. Where are we at here? Where some materials exhibit the phase with the diagram or not, somewhat complicated with the one figure 10.5, and some binary alloy systems. Additionally, with the second component lowers of the melting point, solving the both ends of the phase diagram so that the range of the liquid phase extend with the downward to the middle result with the phase of the diagram, like with figure 10.7 called the eutectic phase of the diagram. It's characterized with the feature of the liquid stable, the temperature of below the melting points of both pure atoms. The important feature of the eutectic phase diagram is the horizontal line, which the liquid region becomes ever more narrow until it finally reaches a point. Line constant temperature called the eutectic temperature of the connects to three important points of the composition alpha phase, which is stable with the temperature of the composition of the liquid phase. All of these phases of the equilibrium with the alloy passes through the eutectic temperature of the liquid phase of the eutectic composition chamber, the two-phase solid mixture over the alpha and beta called the eutectic mixture, or simply the eutectic. All liquid is gone and have been replaced by the eutectic. The transformation of the phases occurs during the eutectic transformation is represented as liquid times the A plus B alpha times the beta. And it goes into 10.5, furious metallurgy. Alright, iron and iron carbide phase diagram shown in figure 10.8 with the base of the all steel with the cast iron metallurgy. Consider the pure iron axis. Over the entire temperature region shown with the pure iron axis exists two different structures of FCC and BCC. Depending on the temperature of the very important report, remember that iron BCC all temperatures at 912 degrees Celsius, at which point it changes to the FCC. Remains FCC until the 1430 degrees Celsius, at which point it returns to BCC until it melts at 1536 degrees Celsius. The lower temperature BCC phase called alpha and ferrite. The FCC phase is called the gamma austenite, and the high temperature BCC is called delta. The phase diagram showing the degree of the solubility with the carbon in each of the three phases. Notice of the ferrite region is narrow, with indicating low solubility with the carbon in austenite region with it quite wide, up to 2 weighted percent of Celsius max, indicating quite high suitability with the free phase occurs at 6.6 weighted percent of the calcium called the ferrous 3 carbon or cementite. Has virtually no solubility with and exists at 6.6 weighted with of percent of the Celsius. Few simple heat treatments available with the ferrous 3 carbon system. Consider first alloy containing 0.7 width of the percentage of the calcium C. Heated above the Euclid temperature of 727 degrees Celsius allows simplification of the austenate with this process called austentation. When alloy is slowly cooled with the Euclid temperature of the austenate undergo the phase of the transformation form two-phase mixtures ferrite and cementite called perlite. The transformation is complete with a microstructure complete with a periodic, and the alloy may continue to cool below 727 degrees Celsius. Heat and treatment called normalization involve the austentation called by air cooling. An alloy contains less carbon than 0.7 width of the percentage called the hypo-Euclid steel. These alloys are austenitized by heating above the average above A3 temperature. The A3 line is a boundary separating the austentated region from the ferrite plus the austentated region for an alloy boundary at A3 temperature, where the slowly called below the A3 temperature ferrite called primary ferrite forms an austentate. When alloy crosses the A1 temperature of the Euclid, the temperature of the remaining austenite transfers to the perlite with the final microstructure, then ferrite and perlite. The inverse lever rule determines relative amounts of the two can constitute. If the alloy is low carbon, says that 0.2 width percent final microstructures, nearly all ferrite, very little perlite. An alloy that contains more carbon than 0.7 width of the percentage is called the hyper-Euclid. Within each steel for the primary purpose of cementite microstructure, these alloys, normalization, cementite, perlite, the cast iron with the iron carbon alloys with containing 2% width percentage was calcium C or more. On the other hand, austenite cooled with a sufficiently fast to avoid with the formation perlite marsenite will form from the threshold called marsenite start temperature. Marsenite is not in the equilibrium phase where chief virtue is potentially high hardness. Hardness of micromartenite is increased with the carbon content, usually 0.8 width percentage of the C, and the Rockwell C hardness steel is ranges from RC50 to RC60. 10.6 Solid solubility in metal alloys. Solute metal atoms reside with a solvent lattice in some of the extent of either two ways, substantially or intersistently. Substitutionally, the solute atom replaces solvent atoms of the lattice side with a very extent varies according to the thermodynamic other factors. For instance, the copper-nickel atoms that can complete exchange with each other with the FCC lattice, and of the conserved with the completely soluble with the copper and silver. On the other hand, can tolerate with a limited exchange, and they considered slightly soluble. Interstitial solute atoms occupy the position between the solvent and atom-solvent lattice. For these reasons, interstitial solutes are limited to small amounts of small atoms such as carbon, hydrogen, and nitrogen. The extent of the solubility limited to only small fraction interstitial sites can be occupied. Vacancy lattice sites, and there is no atom occupying the sites. Every metal has an equilibrium concentration. Vacancy increase exponentially with increasing temperature up to the melting point. Alright, 10.7, the chemical diffusion. Any temperature of any above the absolute zero, atoms are vibrating in lattice position. Atoms can change with the position, move with the neighboring vacancy with the case of the interstitial solute atom and the neighbor boring interstitial site. The process is simple, a jump from one site to the next by the chemical diffusion process. The atoms can be moved through the material. The fixed first law of the give of the rate of the atomic motion termed with the rate with a mass transfer. So law's rate of the atomic motion as dc over dx, which is the concentration gradient solution, with a variation amount of solute at c is the distance of j, the first rate of atomic motion in term in 1 over a times d m over dt with the mass flux for the x direction. The mass atoms moving through the section area of the A and the D of the difference to the constant diffusion solute solvent system. The magnitude of the D indicates the material system. The rate of the diffusion exponential function temperature, since the rate of the atom jumping increased the greatly increasing temperature of the amplitude of the atomic vibration increased the variation temperature of the given at 1014. Our rate of the diffusion is equal to the diffusion constant times the exponential negative activation energy of the material constant and times the rate of the universal gas constant, and T is the absolute temperature. So Higher activation energy, lower diffusion efficiency D, the greater the dependency on temperature. So, some of the interstellar atoms, such as the hydrogen, carbon, small alloys, ion-occupied interstellar sites with the neighborhood activation energy of the lower and diffusion rates higher, several the orders of the magnitude of the substitutional solutes, principally because changes of the neighboring sites making vacant substitutional quite low. Table 10.3 shows the list of diffusion constants, activation energy of the three systems. Alright, 10.8, corrosion. In this section, basic elements with galvanic corrosion metals are discussed. The process of which metal loses mass is called oxidation. In this process, the metal atoms lose one or more electrons, becoming the metal ions expressed in the equation. M result in M to the n plus over number to the E number of electrons. M refers to any metal with the E electrons of the oxidation process occur with the anode. Thus, the simultaneously anode reaction-reduction process must be operating as to conserve the electrons in reaction. In figure 10.16, electrons are consumed. The M plus N equals M, any metal. So the electrons pass through the anode to the cathode electroconduction. The anode to the cathode must electrically connected. Typically, anode reaction as follows. Anode reaction produces metal ions. You have copper 2 electrons, nickel N1 aluminum and helium. Typical catalytic reactions: copper, nickel, aluminum, hydrogen. Corrosions can be viewed with electronic reaction consisting of a combination of the oxidation reduction process half-cycle reactions like those shown above that can be combined to form complete reaction. For example, the zinc and helium anode cathode. By reversing any direction anode reaction with the represent oxidation and combining with the two half-cell of the reaction with a complete reaction could be obtained for zinc and helium chloride, hydrogen chloride, or zinc and hydrogen. And first reaction, zinc of the anode oxidation, hydrogen chloride reduced or liberated to hydrogen gas, surface of the metal conductor, which acts as the cathode in some corrosion. Cell of the cathode half reaction can be plating out metal ions onto the metal cathode. In most cases, however, the cathode half cell reaction involves water or hydrogen. Simple typical cathode reactions are as follows. Determine the relative tendency for the anode cathode pair over the corroded. The concept of the electrode potential used. Standard EMF service series shown in figure 10.4. Electrode potential of the reduction half cell reaction. Various metals listed with the hydrogen gas electrode serving as a reference of the 0 volt. The two similar metals are placed in contact, the one lower than the table of the anode, and corrodes. The care should also be taken to avoid service to similar metals that will be in electrical contact. 10.9, mechanical behavior. The stress-strain curve. The response of the material applied and stress and applied with the strain is called mechanical behavior. The crystalline structural materials from the all metals of the many of the ceramic behaviors is two types: linear and elastic, linear elastic and plastic. Each type of the characterized property of the air relate with the applied stress of the representative of the variable, whatever it may be. Most commonly, these relations between the stress and strain of the relevant property of the measured on the uniaxial stress-strain curve. Keep in mind that stress A or the stress in the case of it defined as fouls, and then shows the chart where load was applied with the axial direction strain, engineering stress of the original area with the true stress of the instantaneous area that it is. Strain is defined as the resultant L length of the original and length of length over stress, or the original gauge length is sample. The true strain is Ln over the length of original gauge length. The original length and the length of the instantaneous length of the increase of the energy stress strain curve of the typical engineering alloy shown in figure 10.9. For some very important property with determined with the elastic module with the yield strength, the ultimate tensile strength of the fracture strain, all clearly exhibit the accurately constructive structure stress-strain curve. Elastic models of the Young models is slope of the elastic portion of the curve in the steep linear region, while E is a proportional constant relating stress to the strain during elastic deformation. The 0.2% offset yield is the stress value The intersection line is called the offset with the constructed parallel elastic portion of the curve, but offset with the right is strain of 2,000s. That represents the onset of the plastic deformation. Ultimately, tensile strength of the energy stress value of the ore. The maximum energy stress strain curve that represents the maximum original area of the sample sustained with the undergoing unstable necking that will lead inexorably to the fracture. The fracture strain of the energy straining value of the fracture curve. However, a lot more information contained in the stress strain stress curve. At the outset, though, clearly distinction must be made between the true stress and the true strain curve and the engineering strain curve. The difference, shown in Figure 1010, which all plotted on the same axis of the stress strain curve of the engineering stress strain curve, same material, but the difference evident with the definition: true stress strain, engineering stress strain. Engineering stress is the load applied to the sample divided with the constant of the original area of the true the stress, the load applied with the sample divided by a variable instantaneous area. Note the true stress always rises plastic region, whereas engineering stress rises with the falls going through the maximum, and the maximum represents a significant difference between the engineering stress strain curve and the true stress strain curve of the engineering stress strain curve. This point indicates beginning of the necking. Hardness. Since hardness is a measure of the material resistance, permanent indentation, loading relation, indentation, depth of the measure of strength, some of the materials have high hardness and the vice versa. An approximate relation between the hardness and strength is as follows. UTS, or ultimate tensile strength of the mass pascals over 3.5, the hardness Brenner number. Ultimate tensile strength, PSI, is equal to 500 over the Brenner hardness number. Plastic deformation, crystalline material. The mechanism: plastic deformation, crystalline material. The motion dislocation through the crystal represents shear stress, adequate level, the magnitude of the stress required for the process of the measure, ease of the dislocation motion of the material with the yield strength, and the crystalline material then can be viewed with the stress required for the beginning dislocation motion. There's an easy dislocation motion, significant amount of the plastic deformation achieved with the material called ductile. It's however there is so much resistant dislocation motion that the plastic deformation cannot occur without the stress rising to the fracture level. Then the material is called brittle. Being strong enough, hard enough is usually associated with it being brittle. Ductility is also associated with less strong. Fracture toughness. Fracture toughness is a material with a property representing material ability to absorb energy through fracturing property. The K to IC is listed as supplemental alloys, table 10.5. The higher the value, the more energy absorbed for the fracture process. The fracture strength of the piece of the material depends on the fracture toughness value of the material, size of the largest crack of the piece, the geometry crack size of the notation, Figure 10.11. The relation to fracture toughness is equal to tensile strength stress times F to the square root of pi times the crack depth of the surface crack. Strength mechanism. The simple yield of the strength of the material has been defined as stress of the plastic deformation beginning with the fall of the means of the dislocation motion could be impeded or relieve the stress required to initiate the plastic deformation, thereby rising in strength of the material of the various processes accomplished for the purpose called the strength of the mechanism. Strain hardening. One of the most common mechanisms of the strength of the crystalline material with the strain hardening. In this case, the dislocation motion becomes responsible for the impending dislocation motion. Mechanism involves two concurrent action with an intersecting of dislocation during the motion impedes with the further motion, and the multiplication of dislocation during the motion increases the rate of the intersection. Therefore, the strain hardening in a plastic strain with a dislocation motion increases the stress required to continue with the motion until always increases. The result observed to be the positive slope of the plastic region of the true stress strain curve, shown in Figure 10.10. Solid solution strengthening. Dislocation more difficult to move through the lattice of the crystalline solid solution through the lattice of the pure crystal. The resistance of the motion increases the solute content, but although these significant variations of the degree of the various solute contribute strength effect of the most solute with a sort of the increase the effect. Therefore, general the purest crystals have a low strength, neglecting strain hardening. Second phase strengthening. Dislocation motion further impeded with a small particle with one or more additional with the dislocation to have a difficulty passing through the particle, therefore must bow bow out between them in order with the continued move of the distance between the particle to determine the strength of the interparticle. Spacing decreases, strength increases. Very common use of second phase strengthening is precipitation hardening group of aluminum alloys known as heat treatable alloys. See the phase diagrams. Aluminum copper alloy typical is shown figure 1012. Dash line is C0 or hardness, brittle hardness, and 0 indicates particular alloy suit with a precipitation hardening treatment. This alloy is heated until a single phase alpha region and the alloy becomes a solid solution. Single phase when cooled into the alpha plus theta region, the theta phase of the precipitates out of the solution dispersion throughout the matrix. The alpha solution is called slowly large particle of the theta form. Alpha is coolly rapidly room temperature formation of theta is suppressed. Finally, supercooled alpha is reheated with a relatively low temperature. Theta is nucleated with grow and the very fine dispersion within the alpha matrix with fine dispersion with small interparticle spacing contributed significantly to the strength of the aluminum alloy. The designation second phase strength heating is 2 is T6. Grain refinement, fine grain polycrystals are strong with the coarse grain polycrystals because of limited volume with the crystal. Small grain impeds dislocation motion. Higher stress is required with small fine grain from the same amount of dislocation motion, large coarse grain. The ASTM number scheme quantified with the grain size with the grain size with designated with the number 1 to 10. The larger number, the smaller the size, the quantitative relation with the given in the equation n. The average number of the grains per square inch is equal to 100 at 100 magnification. The n is the ASTM grain, so it's the average number of the grains per square at 100 magnification, and 2 to the n of the ASTM grain size number minus 1. Quenching and tempering marasonite. Temperature marasonite is one of the most effective of the strength phase of the found with the material of the crystal structure of the marasonite, but it's more complicated with the structure of the more metals. More metals and microstructure very fine with the beginning of the mineral which of the marasonite form with the during the temperature fine precipitation carbide with the contributed to the strength with the hardening. In addition, a large amount with the carbonated solution even after the temperature of the phase the strength of the solid solution. Clearly, many with a different mechanism contribute with the strength of the marasonite hardenability. Transform the austenate marasonite with the sensitive of the cooling rate, with the quenching of the process of the cooling rate, sensitivity of the function of the composition of particular steel. For example, the plain carbon steel with the mass be called cooled very rapidly, some form marasonite. The highly alloyed steel such as the SAE 4340 can marasonite, which may be cooled with much more slowly. The sensitive of the cooling rate with the kind of hardenability measure of the report of the Jomny N quench test. The steel with a high hardenability cooling be cooled slowly with the chill form marasonite. Therefore, quenching can harden large sections of the steel with even slow cooling rates at interior. On the other hand, steels with low hardenability must be cooled very rapidly to form marasonite. They're only small sections of these steel that can be hardened in the interior because of the cooling rate, but during quenching they must be kept high. Annealing, most alloys undergo plastic deformation. Length of the dislocation crystals increase the proportion amount of the plastic strain that the dislocation possesses elastic strain energy proportion with the length of the dislocation length of the increase of the total energy of the metal. The increasing elastic strain energy with is called the short energy of the plastic deformation. Plastic deformed piece of the metal is heated with a temperature of about half of the melting point of the degree in Kelvin, 1/2 the absolute melting temperature of the material. With the short energy of the plastic deformation over the process of the new grains over the new formed midst of the deformed grains. For these new grains have the same dislocation distribution as present performed with the plastic deformation, and therefore they have original strength and hardness. Each of the new grain grows outward to consume all of the deformed material, replacing new grains. For this way, the anneal pieces return to the original strength of the ductility process called the recrystallization, one of the most common annealing processes. Cold work versus hot work. When metal alloy is plastically deformed at a temperature above the half its absolute melting temperature of the recrystallization curve, the simultaneous with the plastic deformation situation referred to as hot working. Strain hardening cannot occur during deformation. On the other hand, plastic deformation carried out with a temperature below 1/3 to 1/2 the absolute melting temperature referred to as cold working is accompanied with the usual straining hardening. 1010 magnetic behavior. Magnetic behavior material divided with generally three groups: diamagnetic, paramagnetic, and ferromagnetic. An uninformed person refers to the material being non-magnetic. He or she is referring without distinction with the first two types of the behavior of the material. Said with the magnetic, its behavior is the ferromagnetic. All material of the electron over the atom's magnetic moments, and because of the motion above the atoms of their own axis of spin, as these the motions produce a small magnetic moment of that which in the applied magnetic field is cancelled with the magnetic field is applied. However, there is one type of the material that experiences alignment with electronic magnetic moments of the applied field of the behavior is diamagnetism. And other type of the material of the weak of the permanent magnet moments of the atoms align with an applied magnetic field. This behavior is called paramagnetic. Both of the magnetic response to the magnetic field of the non-permanent and weak. When applied, the field falls to zero. The net magnetic moment of the material also becomes zero. And copper and silver magnetic, while aluminum and titanium paramagnetic with the insert metal of the iron, cobalt, and nickel with their alloys are quite different material with the ferromagnetic. Observed within these material with the magnetic moments of the electronic spin aligning themselves within the atom from atom to atom, resulting in strong magnetic moment in absence of supply with the magnetic field. If all the moments of all of the atoms align themselves with the cross of the bar of such material, the result would be a permanent magnet with a north and a south pole. In some cases, these materials, however, bar divides into domains. Each domain, which is contained along atoms with the possess north and south poles, which is exactly covered with the north and south of the pole with the neighboring domains. The bar would thus have no moment that even though each domain was permanently aligned with the magnetic fields applied. However, the domain boundaries reposition themselves to create the net magnetic momentum to align with the applied field. Now, if the material's hard and magnetic domains do not return to the original size and shape of the bar, will then be a strong permanent magnet. This material if the material is a soft magnet, the domains and reposition themselves when applied. Field is removed, so that again there is no magnetic moment. In most material, the difference between the hard and soft magnets is the microstructure. The microstructure effect is either the motion of the domain will boundaries called the block walls. Thus, electromagnetic soft magnet with the meaning of the applied field can control the magnetic moment of the moment. The magnetic permanent magnet with a hard magnet with a net magnetic moment is always present because of the main boundaries are prevented by microstructures from moving. To test the material for the magnetic behavior, the paramagnetic, you test the magnet. If the test magnet is attracted with the material with the ferromagnetic, if no attraction occurs with the material with either paramagnetic or diamagnetic, two types cannot be distinguished by field. Ferromagnetic materials lose ferromagnetic behavior because of the paramagnetic when heated above the Curie temperature. For iron, this is 768 degrees Celsius, just below the BCC and AA and at minus FCC wide transformation temperature, 912 degrees Celsius. And steel for the FCC Y phase for the ostentated can be as low as 768 degrees Celsius. In such cases, the paramagnetic behavior is related to the structure, not of the temperature of the shape of the ostentate, even the low temperature of the will paramagnetic rather than ferromagnetic. 1011 Electrical behavior. The electrical behavior of the material is divided among four types of metal conductors, insulators, and semiconductors, superconductors. Metals and metal atoms are held together with metallic bonding, very complicated process with important consequence, high electrical conductivity. Binding mechanism produce free electrons which are not bound to any particular atoms of the solid, hence the term is free. And this free electrons that give the rise to high electrical conductivity. Governing law conducted by Ohm's law with the volts are equal to amps over the resistance of the ohms. R depends on the cross-sectional length of the conductor, but not more material property are shown in the relation, as in the resistance of the ohm is equal to the resistivity of the ohm meters and material length over the the amps. P is the resistivity of the ohm meter of the material, with the thus material property deduct for the material A, the reciprocal P. So amps are equal to 1 over the P reciprocal the conductivity ohm meter to the negative 1. If the conductivity considered with the motion charge with the carrier with the electron, example, the conductivity of the conductor is given in an equation as conductivity equal to the N to the E, the absolute times the U. N is the number of chains carried with the unit voltage free electrons in the metal. E is the absolute electron charge, and U is the chain charge of the mobility. In this case, the metals carrying concentration of number of charge carrying the ultimate unit volume remains constant with the multiple of the charge mobility decreases the temperature increases because of the increase of the frequency collision with the electrons with the increase of the amplitude of the atom vibration relationship results in the rule of the four of the metals resistivity increases the temperature increases. In fact, the rule becomes basic of the definition of a metal. Insulators. Some materials, such as the diamond and UV, involve the covalent bonding electrons to bond with their atoms without, and so there are no free electrons or the atomic at the end in equation of the 10.28 to nearly zero. The result of the negligible conductivity, very high resistivity of these materials will act as insulators, semiconductors. Some materials called semiconductor, the electrons are bound with will increase the temperature of the and/or applied voltage of the electrons can be excited with allowed with the unoccupied energy state. In such a state, the electrons can be a free conduction electron with a very excitation event. These are produced with a vacuum-bound state with the bounded with the electron excited with the conduction state, with the other bound electrons with the migrate vacant bond state called the whole, given the rise of electronic mobility with the conduction. However, the case of the convention assigned to the positive of the current to the whole motion. Even though the electrons are moving, the situation can be compared with the moving the line of the chair of the one chair vacant. If the person moved the vacant chair when it arrived next to him, the person's electron will be moving, so say from the left to the right, will be the vacant chair of the whole will be moving the right to the left. In intrinsic semiconductor, such as the pure silicon, the number of the free electrons and the number of the holes are always equal. Very important to the concept of these semiconductors. Equation 1028 of the term end of the carrying concentration increase with the increasing temperature because of the increasing number of the excited electron. The increase is very much larger than increasing mobility. With the net result, the increase the conductivity. Therefore, with the conductivity increase the resistivity, decrease the temperature of this. Basis for the definition of the intrinsic semiconductor, the disfinite converse of the metal definition, and microelectronics extrinsic semiconductors are common ones. These are impurity atoms called the dopants, control of the carrier of the concentration selected to dilute the atoms of silicon. For example, the fully positively ionized room temperature provided with the free conduction electron per dopant atom. In this case, the free electron concentration remains the rough conditions constant equal to the dopant concentration. In this case, the dopant atoms contribute electrons to the conduction process of the semiconductor. It's called the N-type. For the N is for the negative electron conduction. However, another type of the dopant can be fully negatively ionized with the room temperature dissolved with the silicon with the will capture with the bond electron through with creating one hole per dopant atom. In this case, the dopant silicon is P-type or positive type hole conductor. But the form case of the dopant atom is called the donors. In the later case, they are called the acceptors. Remember that donor type negative is donors and positive type is acceptors. Where P-type semiconductor electronically joined with the N-type semiconductor, the P and N junction is formed. The junction is called the diode. Passes the current proportional voltage forward phase bias, whereby the voltage is preserved. The junction called the diode passes current proportional to the voltage where forward bias, but when voltage is reserved for reverse bias. Diode passes only in small constant current. The behavior is the basis of the operation solid-state rectifier. Alright, moving on to superconductors. Limited group of the material composed of the metal with the trimony display with a very complicated behavior of the trimony of a superconductor. Where these materials are cooled below critical temperature, reserves if it drops to nearly zero temperature. Critical temperature is shown in Figure 1013. Range of the critical temperature extends to low temperature 1 Kelvin for some niobium alloys high, approaching at 200 K for some newer ceramics. 1012 engineering materials. Might be able to finish this. In addition, the metal the alloys cover the previous section of the behavior section and will cover the aspect of the glass of the polymer composite of the glasses. Atom molecule that cannot arrange themselves with an orderly array with the control of the amorphous of the structure in the case of the most liquid the maneuver the solid with the display of the amorphous structural characteristics. Such solids are called glass. The most familiar with the sodium lime glass as silicon oxide 2. Atom groups along with the sodium calcium ions bound with a variety of the wave with the regular array is rarely attained. Unlike crystal glass does not exhibit the melting points rather than undergo the gradual transition from solid to viscous behavior. The time dependent flow of the temperature of the transition begin with the during the heating of the glass transition temperature Tg. Glass is brittle with the temperature below Tg. Some dislocation of the extremely difficult to move with the glass transition temperature with the material gradually becomes viscous. Viscosity decreases the temperature with the increase until the upper limit of viscosity is of the common liquids just above the transition temperature of the viscosity with extremely highly displayed with the leathery behavior of the type of the well-known glass blowing process. There is no sharp transition viscosity in this region. Polymers. Polymers are material composite of a long chain of the molecule with a chain with the principally bonded with the gap of the means with the weak of the intermolecular bonds resulting in ease of which of the chain slide relative to one another is the origin and low strength of the polymer of the chain with the nature of the molecules also with the difficult of the polymers to crystallize as so with the amorphous of the particle partially crystalline. The structure of the polymer changes greatly among polymers. The strength of the intermolecular bonds determined with the degree of the irregularity of the chain structure called polarity. For example, the most regular chain structure, the lowest polarity with the found with the polyethylene. These chains, but not most liquidly bound with the irregularity of the side of the group. The increase of the polarity increases the bond with the strength increases. For example, the polyomethyl methacrylate. Properties are high in bond strength with the glass transition temperature with the interpreted with the temperature at which the unchained with the bond with the begin with the break during the heating of the foul with the weaker of the bonds also with the temperature gray glass. General polymers fail with either two glass of thermoplastic or thermosetting thermoplastic are those who with the chain with the interconnect with the weak of the intellectual bonds for the heave with above the glass transition temperature because of the viscosity can evenly shaped, cool near the below the transition glass transit temperature of the non-viscous solids related to the shape. The example of the glass polyethanol, polypropylene, polystyrene, nylon. Glass transition temperature for several of the polymers are shown in Figure 10.6. Remember that polymers have the glass transition are brittle. In thermosetting, polymers change with addition with the interconnected strong covalent interatomic bond cross-linking. Cross-links can be the direct interatomic bonds between the chains or short chain segments of the chain. The longer chain with these cross-links are the difficult break ability of the chain with the slab of the pass. Each of the permanently greatly reduced with the non-completely removed. Only cross-links are placed with the polymer is cured. The polymer cannot undergo any shape change even if the increased temperature. This always means with the brittle. For example, the class of the two part with the polymers, epoxies, and polyester resins. Rubber is also a thermosetting polymer. Vulcanization, one of the cross-linking processes, but rubber and long chain metals are tightly coiled, along large elastic deflection with no permanent shape change. Composites, composite material mixture of the two or more mutually insoluble phase of the produce. The methods for the other phase of the transitions. Heat treatment is promising benefit with the materials live with a variety of the combination properties and shapes that cannot otherwise obtain with a conventional material so that involved the use of the fibers embedded in the binding matrix of some fiber reinforced polymer bundles. Other particles mixed within the minority binding phase, such as cemented with the carbonides. Composite structures usually design an optimized relation between material properties and surface requirements. Physical property composite usually follow with the rule of the mixture where the total property with the composite with some of the products of the volume fraction. Each components of the property, for example, the density, specific, the heat, with the capacity of the composite, may be determined as follows. And although the rule of the mixtures is you have mixtures is used with the approximation mechanical property composition more difficult to predict with the mechanical property components because of the composite complexity, particular shape, and interaction. These materials were capable of displaying significant anisotropy, or the condition in which physical and/or mechanical properties vary the direction with the material, especially with the fiber-reinforced materials, wherever the fibers are aligned. The wood is example of the natural fiber and reinforced composite material. Concrete is a common composite involved with a pre-designated mixture of the Portland cement and the water with the aggregated such as sand or stone. The Portland cement reacts with water, undergoes hydration to form a three-dimensional solid network. Calcium with aluminum silicates. Strength of the set concrete depends on water-cement ratio. The higher the ratio, the lower the strength of the cement. 10-13 lower the strength of the concrete. 10-13 summary of the chapter is covered with the summary form of the important topic of material science, engineering, the material presented with the intent of the review of the important material, and not effective in the introduction any of the topic of the anti-structure, the bonding of the critical crystal structure, corrosion, phase, equilibrium, including various metallurgy foundational topic. The first part of the chapter review moves to mechanical, electrical, mechanic behavior, followed with a brief reviews of the polymer and composite materials. And that's chapter 10.